Hello, good morning everyone. Today we will go through the chapter beam equation. Previous chapters we have derived the FEM equations for prismatic bar. The methods that we have used is the direct method. However, we can also apply the potential energy methods as well as several other principles such as Gallatin's residue methods. This will only prepare you for some knowledge, okay? Today our main objective is to apply a beam elements. A beam elements, as we have used previously, we can always form a stiffness, okay? Instead of a prismatic bar, we can use a beam. So a beam is defined as a long, slender structural member that's subject to transverse loading, which is a vertical loading that produce significant bending. Therefore, there will be a moment as a load as well. Hence, there will be 2 degrees of freedoms considered per node, which is transverse displacement and a rotation. Consider the beam element itself. It will have 2 nodes, and each node is subjected to the local transverse nodal as well as rotations given by the phi, okay? The local force will be acting at each node as well as the bending moment of M. In the beam element itself, axial effect is neglected. This is the basic sign convention that you have learned previously in strength of material, okay? In order to derive for the beam stiffness, we will apply the so-called famous Euler-Bernoulli beam theory. In the Euler-Bernoulli beam theory, we would assume that the plane across sections perpendicular to the longitudinal axis before bending and after bending remain a plane, okay? So meaning to say, the cross-sectional area will not have significant shape change, okay, in order to maintain the moment of inertia. The The differential equations would be as such. Okay, the summations of forces and the summations of moment would be equals to 0 to maintain the structure in a static. These are the familiar derivations of it, okay, which you can look through them. So here we will want to apply the beam elements for our finite element purpose. Here we will select the elements. An element itself would have forces and moment acting for a beam, okay, at node 1 and node 2, okay, assuming this is a single element, okay. So always remember, load would only apply at the node, okay, only apply at the node. Right. So here, since we have 2 degrees of freedom per node, therefore we would assume a simple displacement function that contains a1 until a4. So we will express them accordingly and form these relationships. So here we will always assume a small rotations angle in order for the beam theory to hold, such that the cross-sectional area will remain constant. So our objective, again, from the displacement function, we would want to know what is the shape functions, okay. So here the shape functions obtained is given as such, right. We would also note that the summations of shape function at one particular node or position should be equals to 1. Therefore, in this case, let's take node 1. At node 1, when we consider the shape function at node 1, n1 would be equals to 1 and n2 would be equals to 0. Okay, that holds summations of shape functions at one particular node will be equals to 1. Okay, here we will also define the strain, displacement, and stress strain relationships as given, and these relationships are derived based on the previous beam theory. So accordingly, we would derive the element stiffness matrix as such. These relationships between the nodal force and the nodal displacement are formulated in so-called a matrix again. Okay, so this represents the nodal forces, the stiffness matrix, as well as the nodal displacement. Axial effects are neglected in the beam equations. If we would want to extend the effect of transverse shear, then we would apply the Timoshenko beam equations, okay, which will include the so-called the shear corrections. All right, we would not touch much in this, okay, just for knowledge. Finally, we will assemble the element equations to obtain the global equations and solve them simultaneously when we know the boundary conditions. Okay, so take these simple examples. Element 1 and 2 are connected at node number 2. Okay, so at node number 2 we will see that there are loads acting at node number 2, therefore we would apply a so-called additional node here. Alright, so what we need to do, we just form the respective stiffness matrix for every single element. Okay, for node number, or for element number 1 is connected from node 1 and node 2, whereas for element number 2 connected between node 2 and node 3. Okay, assemble them together as the previous direct stiffness method, you will obtain these equations 4.2.3. Now when we consider the fixed support at node 1, there we would have displacement at node 1 equals to 0, rotation at node 1 equals to 0, and displacement at node 1 equals to 0. Okay, at node number 3 we would not allow displacement in the y directions, but we would allow rotations, therefore here we would have the v3 equals to 0. So apply them into our equation, solve them simultaneously. We would solve for the F1, F2, M2 and M3 respectively. No, we will solve for these 3 parameters respectively. Alright, so these several examples will shown the basic idea of how you can solve them. Alright, so the exact detail of solutions you can refer to book. Okay, so the idea is that if you are given a problem where you have a fixed support, a cantilever beam, at the middle we have a roller support, and at the end we have a force. So in these cases we have no choice but to break them into 2 elements, element number 1 and element number 2. Okay, as shown in picture. Okay, because whenever we replace the support, we will reveal the reaction force. Okay, so we will have reaction forces and as well as moment. Okay, so all these loads must be acting at a single node. Okay, so similar to this example number 2, we have a long bar itself connected, okay, as such. Okay, so here we have no choice to break into nodes for every single point where there will be loads acting. Okay, so we will break them into 4 elements, element number 1, element 2, 3 and 4. For example number 3, similar case. Okay, we will apply a beam stiffness matrix for element number 1 and number 2. Okay, where you have a reaction force and moment at node 1 and 2. Okay, however at node number 3 there is a spring connecting them. Okay, so to represent this particular spring, we would apply a spring stiffness matrix to represent the so-called element number 3. Okay, so we would again solve them accordingly. In many cases there will be a disputed load acting. Okay, so what we would do, instead of not only disputed load, okay, and concentrated load, what we would do, we would want to resolve these forces to the nearest node itself. Okay, so we would want to transfer this into the nearest node. So if we do not want to add any additional node at the middle, okay, then we will have to transfer them into the equivalent moment and force at both end of the element itself. Okay, so how we could do that, we would break them into this is the idea of another part. Okay, we have disputed load disputed to the nearest node itself. Alright, so the idea is we would use the work equivalent methods to replace the distributed load to the discrete load. Okay, so this is our displacement functions as we have obtained previously using the displacement functions equations. Alright, so the work for a disputed load will be given as the summations of the load acting along multiplied by the displacement, right? So force the work done is force multiplied by displacement, so we have this integral, right? So again, if we want to bring them into a discrete nodal force, okay, so we would want to have the moment and the rotation itself, okay, related to this, okay, and then the force and the displacement itself represented by this, right? So similar to the other side, okay, so to the other side, okay, so we will have this particular part, okay, we will discretize them together. So here, once we discretize them together, we will assume that they should be equals or equivalent, right? So this is where we form our main equations. Okay, so here we have to evaluate this particular left hand side as given as such. Okay, so how to evaluate? We just take the so-called mathematical equations, so put this in, okay, then multiply them together and integrate with respect to x, then we take the so-called finite integral of them, we would get this. Alright, so this part will be equals to the so-called discrete regions. Okay, so what we would do now to obtain the M1, M2, F1 and F2, we would now just set rotation for node number 1 equals to 1, then the rest equals to 0, then we would review the M1, okay, taking into account that the length is equals to 1, right? Then similar to others, okay, we will take rotations at node number 2 equals to 1 with the rest equals to 0, okay, to get the moment at node number 2. Okay, so same thing, okay, displacement 1 equals to 1, review the force at node number 1, displacement at node number 2 reviews the force at node number 2. So here we will see examples on how to deal with it. Alright, so this is a fixed free end cantilever beam problem with a disputed load. Okay, so we would break them into two discrete part of load. Okay, so we discretize the beam. Okay, here we only apply a single element, okay, to represent the whole beam, and similarly we have the force equals to K and D, right? So this force itself is just a summation of all the forces acting at node number 1. Okay, so at node number 1 we will have the so-called forces, okay, acting. So we have the reaction forces, okay, F1, Y, as well as the moment 1. Okay, so we will see that at node number 1 we will have this F1 Y minus WL divided by 2, right? Okay, same thing for this, whereas for at the free end this will be 0 and 0. All right, so now we apply the boundary conditions for the fixed end itself. No rotations and displacement allowed, therefore we will now solve for the displacement and rotations at node 2, okay, as given as such. So we can simply solve directly, okay, but then if we want to structurize the algorithm itself, then we would see this so-called this so-called effective global nodal force itself, okay, as represented by this K multiplied by D. So this is the ideas, okay, whereas from the so-called free body diagram that we have derived, we would see that this force actually contain two parts, okay. So this particular part, okay, which is all the forces that you will need to find, okay, as well as the parts contributed by the distributed load and the final part, okay, this is the KD part. All right, so if we move this over, we just have to minus it out, right? So what we do, we just minus it out and we review the solutions. If we don't want to do this, okay, we just solve it as usual, okay. You still get the answer where, again, very obvious, F1 F2 equals to 0, okay, since nothing is there. So in order to verify the summations of forces and the moment should be equals to 0. Okay, this is this slide shows the ideas, okay, of how we can apply the beam equations, okay, or beam element itself, as well as the distributed load ideas, okay. So we can, even it is not a distributed load, we can also separate them into two nearest node itself, okay. Since this is a concentrated load, if we do not want to add an additional node at the midpoint of this beam, cantilever beam itself, we have no choice but to separate them into two parts, okay, equivalent loads, discrete load at both ends of the element. Okay. Then similarly, if you can easily derive for a uniform distributed load, then you can also try out on the non-uniform distributed load, okay. We just have to break them into parts if you would want to, right, into the equivalent discrete loads. All right, so finally we would want to compare the solutions of our finite elements with the exact solutions of the beam. Okay, so take this as an examples. Okay, so what we would assume, we have solved them out. Okay, so this diagram represent the displacement diagram. All right, so displacement diagram similar to the previous prismatic bar. Okay, so the solutions for the displacement will match the theoretical part at the node. Okay, at the node itself, right, at the node itself. Okay, but there will be an additional arrow in between, okay, along the other length. Okay, for the moment diagram itself, then the best approximation point would be at the middle. Okay, at the middle itself. Okay, so always remember this is a single elements, finite elements. Okay, so the best bending moment appears at the midpoint, where the bending moment is derived by taking two derivatives of the displacement itself. Okay, so this gives us the bending moment. Okay, so therefore it would take more elements to actually model this second derivative. Okay, similar to the shear force. Okay, so this shear force is a three derivative itself, therefore we would obtain a straight line, a constant line. Okay, from a curved line. Okay, from a curved line then become a straight line when we differentiate them, and when we differentiate again we obtain a constant, right? Okay, so the best point again to approximate this would be at the midpoint. Okay, the midpoint itself. Okay, so you will see that the error increase at the end of it. Okay, at the end of the element itself. Okay. So in order to improve the finite element solutions, we have two choices: either to use more elements, which is involving refining the mesh locally, alright, perhaps, or to use a higher order elements. Okay, so higher order elements we would have like elements with a midpoint. Okay, so this midpoint elements, since every single elements contain 2 degrees of freedom, so they would have 6 degrees of freedom. Okay, that would give us a fifth order approximations. Okay, from A1 to A6. Okay, so by using this, hopefully we would able to solve for or improve the solutions. Okay, so these are some of the tutorial questions that you can try it out at home. So thank you, and hope you would be always ready. So every single knowledge that you learn today may not be applicable, but that will prepare you for to be ready. Okay, so when you are ready and there is an opportunity, then you will obtain a good luck, right? Okay, so similar to this so-called situations nowadays. Okay, if we do not have, or those companies do not ready with the online platform itself, what happen is that they will no online or virtual class. Okay, because when there is this opportunity or needs, they are not ready. Okay, so always get yourself ready, and when opportunity comes, then there is where your luck comes. Thank you.